Hello again. So in the last lecture we studied the definition of an orthogonal matrix, and an orthogonal matrix was defined by this condition: A transposed A equals I, and A is an orthogonal matrix or we can say A is the matrix associated with an orthogonal transformation. Right. Why do we care about these matrices? Let's let the cat out of the bag. Because rotations and reflections are orthogonal transformations. So we're going to set this up in a second. Let's first consider these orthogonal matrices in general and derive a few of their properties. And from those properties we will see, in fact, that orthogonal matrices are of exactly two kinds. Either they are rotations or they are reflections. So let's figure this out. So let's take this relationship A transposed A equals I and derive some consequences. So one consequence is some properties. One is that A transposed is A inverse. I showed that last time. Second property is based on the fact that we will show that the determinant of A is equal to plus or minus 1. How do we show this? Proof. Whenever we have matrices, if C is equal to AB, if a matrix C is the product of matrices A and B, then determinant of C is the product of determinant of A times the determinant of B. Okay, so let's apply that relationship here. So therefore, determinant of A transposed times the determinant of A is going to be equal to 1. So we showed that the determinant of A transposed times the determinant of A is equal to 1. Now we know that the determinant of the transposed of a matrix is the same as the determinant of the matrix. So therefore determinant of A squared is equal to 1. This implies that the determinant of A is equal to plus 1 or the determinant of A is equal to minus 1. So this is a very important property because we have a name for these two kinds of matrices. When the determinant of A is plus 1, we call that a rotation. And when the determinant of A is minus 1, we call that a reflection. And in a little while you'll see why we chose these terms. But for now, you can just see that for any orthogonal matrix, it must be the case that the determinant is plus 1 or minus 1. We just give names to these two categories. We call one of them rotations and the other one reflections. Okay. Okay, let's study another property. And this is going to be that the columns of A are orthonormal. Okay, what do I mean by that? Let's first write out A. So A is some matrix, and let's say that, let's do it in 2 dimensions. So let's say that this is some vector A1 and some vector 2. So for 2 by 2 A. Okay, so far so good. Now, what do we know about such a matrix? What is A transpose going to be? A transpose is going to be a row vector corresponding to A1 and a row vector corresponding to A2. And we know that A transposed A is equal to I. But let's calculate what A transposed A is. And let me switch to a different color. What is A transposed A? A transposed A is going to be this. Let's figure out what those entries are going to be. This entry is going to be A1 transposed A1. This entry is going to be A2 transposed A2. And this entry is going to be A1 transposed A2, and this will be A2 transposed A1. Okay, but the key point is that this product of A transposed A is equal to the identity, and this tells me that therefore A1 transposed A1 must be equal to 1. A1 transposed A2 must be equal to 0. And the same is true for A2 transposed A1. And A2 transposed A2 is equal to 1. So let's repeat what we said. A is equal to, so A is A1 and A2. These are column vectors. And we showed that okay, but what does that mean? That means that the columns are orthonormal. By that I mean, what's the length of A1? What's the length of A1? It is the same as the length of A2, and this length is 1. And that follows from this property and from this observation that we had. What else do we know? We know, so therefore each column is of length 1, and we also know that A1 transposed A2 is 0. And where did we see that? We saw that here. So that says that each column is of length 1, and if I take the dot product of 2 of these columns, that gives you 0. So it's a very pretty situation. This means that essentially A1 and A2 are vectors of length 1 which are mutually perpendicular. So in other words, you can use A1 and A2 to make an orthogonal basis. And this is going to be true in any dimension, in dimension 2, dimension 3, and so forth. So in dimension 2, so let's take up the case of dimension 2 in R2. if we have that A1 is a column vector which is of length 1, A1 is cosine theta sine theta. We can pick such a vector without loss of generality because we know that A1 has to be of length 1, so we can just call this cosine theta sine theta. Okay, then what must A2 be? Well, we know that A2 should also be of length 1, and A2 has to be, the length of A2 should be 1, and it should be the case that A1 transposed A2 is equal to 0. So what choice do I have? I essentially have two choices now. I can make A2, so that gives me two choices for A2. Either I could pick minus sine theta cosine theta, or I could pick sine theta minus cosine theta. So I really have only these two choices, because the property of these two choices is that they both have length, they are of length 1, that's easy to verify, but in addition they are perpendicular Okay, but what does this mean? This essentially tells me that the matrix A, I have only two choices of this matrix A. This is one choice, cosine theta sine theta minus sine theta cosine theta. This is one choice. Or A is cosine theta sine theta sine theta minus cosine theta. This is the other choice. And that is it. The matrix A as an orthogonal matrix in two dimensions can be only these two forms. Okay, let's calculate what the determinant of this matrix is. What's the determinant here? If you work it out, cosine theta times cosine theta is cosine squared theta plus sine squared theta. The determinant here is plus 1. In this case, what is the determinant? It's minus cosine squared theta plus, minus sine squared theta. So the determinant here is minus 1. And recall that I said that for any orthogonal matrix, the determinant is either plus 1 or minus 1. And let's now try to get a physical picture of this. So suppose we have a vector xy, and then consider A times xy and IA cosine theta minus sine theta sine theta cosine theta times xy. And this is really counterclockwise rotation by theta. Which is very nice. So we have, you can convince yourself that this is true by starting off with what happens to the vector 1, 0. So one zero get transformed. And the answer is it gets transformed to cosine theta sine theta. So if we want to set up a little diagram, So if we had this initial vector, then after this rotation it's going to go to this angle is theta, and if we had a vector here, that vector is going to go to, so this is counterclockwise rotation by theta. So in 2 dimensions, the story therefore is very simple. Just two kinds of orthogonal matrices. And these are of the type cosine theta minus sine theta, cosine theta, or cosine theta, sine theta, sine theta minus cosine theta. These have determinant +1, determinant -1. These are rotations, and these are reflections. Okay, I'm not going to derive this here, but you can verify that the reflection matrix here corresponds to reflection around the line with angle theta equals, with angle theta divided by 2. Okay, so now let's go to 3 dimensions. In 3D, we'll consider the basic properties of rotations. So we are going to have again a matrix with 3 column vectors A1, A2, A3, and by a similar reasoning as in the 1D case, as in the 2D case, sorry. The length of each of these column vectors is going to be 1, and the dot product of any 2 of them is 0. So in other words, A1, A2, A3, they correspond to a nice orthogonal basis rather than orthonormal basis, because each of these is of unit length. Now in the case of 2 dimensions, we could characterize a rotation by just one angle theta. In 3 dimensions, it's a bit more complicated. We need to specify a rotation in a more complex way. And it turns out that we need 3 parameters to specify a rotation in a rotation in 3D. So let's see if we can convince ourselves of that. How do we think about this intuitively? And we'll think about it algebraically as well. So intuitively, how will you specify a rotation in 3D? We need to specify an axis about which the rotation takes place, and then we need to specify an amount of rotation. So how many degrees of freedom does the axis have? Since the axis is a unit length vector, this means that we need two parameters to specify the axis. The rotation is some angle, so that's 1. So therefore we need 2 plus 1 equals 3 parameters. So that's one way to think about it. Let's think about it another way, looking at the matrix. From the matrix, how can I choose A1? How many degrees of freedom do I have for choosing A1? We can choose A1 by specifying two parameters. The reason is that the length of A1 is constrained. It must be of unit length. So therefore I can pick A1 with two parameters. Then how many parameters do I have for A2? A2 has to be perpendicular to A1. Okay, so that in fact specifies a plane in which A2 must lie. It has to be of unit length, so I just can choose where in that plane to pick this unit vector. So I will get one parameter. And once I've picked A1 and A2, the third vector is constrained. It has to be perpendicular to both of them. So in fact, it's going to lie along the vector product of these. So A3, it adds no new parameters. So if you add it up, we get 3 parameters. So this algebraic way of looking at the columns of the orthogonal matrix and using the fact that the columns must be orthonormal gives us the same count, that there are 3 parameters which are needed for specifying a rotation matrix. And I got exactly the same count 3 when I considered the fact that any rotation has to be specified by an axis and an amount of rotation. In the next lecture, we'll continue with how we can specify rotations in a convenient way in 3 dimensions.